afternoon, colleagues. Welcome to the first seminar of the Research at Fast Seminar Series 2021-22. Research at Fast Seminar Series aims to explore collaboration opportunity within PolyU community and also serve as a platform for colleagues to get to know FAST researchers. 8 seminars in 4 themes will be organized in the coming months. We hope colleagues will actively interact in the seminars and cross-disciplinary research collaboration could be nurtured. The theme of the first 2 seminars is material science. And for today's seminar, we are delighted to have invited 3 colleagues from AP and ABCT to share with us their research insight on 2-dimensional quantum materials. While Professor Huang coordination of the first 2 seminars, will introduce the speakers and their presentation further later, I would like to thank Professor Huang for his support to make the seminar happen. Professor Huang joined the Hong Kong Polytechnic University in 2004, and he is the professor now at the Department of Applied Physics. His research interests focus on material for electrochemical energy storage and conversion, and emerging ferroenergy material, which for energy storage and conversion applications. With the research expertise of Professor Huang and our 3 speakers, I believe today's seminar will be an engaging and fruitful one. Now, please join me to welcome Professor Huang. Professor Huang, please.
Thank you. Today we are going to have the first theme research seminar on 2-dimensional quantum materials, from pure inorganic to organic-inorganic hybrid. As we know, the 2-dimensional quantum materials are now the first theme the research seminar will be on 2-dimensional quantum materials, from pure inorganic to organic-inorganic hybrid. As we know, 2D quantum materials are now becoming a very hot research topic, which provide a material platform with tunable quantum states. Taking the Twistronic as an example, which is formed by 2 layers of graphene twisted by a magic angle. It shows a very fascinating physical properties. Today, we are greatly honored to have 3 experts in this area to share their experience on 2-dimensional quantum materials. Dr. Cai Yang will be the first one to talk about 2D layered transition metal dichalcogenide with atomic level thickness and dangling bond free surface for applications in low power transistor, negative capacitance field effect transistor, complementary NC logic inverters, and Van-Waals metal gate transistors. Then the second speaker, Dr. Len Kai, will talk about an emerging field on molecularly thin 2-dimensional Randerson purple perovskite, which herald new opportunities for tailor-made semiconductors. Monolayer 2D perovskite with single quantum well show novel optical properties compared with their counterpart. There is a need to understand thickness-dependent electrical, excitonic, and photonic properties that go beyond quantum confinement effects, and scanning probe microscope and photoluminescence spectroscopy will be applied to study the order-disorder transitions on single and field layer perovskite quantum wires. Finally, Dr. Wang Bolong will present his theoretical investigation on the optoelectronic properties of 2D materials. He will highlight the significant roles of electronic structure in modulating piezoelectric, photoelectric, and charge density disturbance for various kind of 2D material, including TMD, oxides, and heterostructures. Now, let's join me. Welcome the first speaker, Dr. Cai Yang.
Thanks very much for Professor Huang's nice introduction. It's my great pleasure to attend the first FAST seminar series. two-dimensional quantum material. So what is two-dimensional material? Two-dimensional material actually, in one direction, its thickness is pretty low, close to the atomic 6 level. So with this quantum confinement effect, this new material can exhibit some unique physics and chemistry property that are not available in 3D bunk material. So with this new unique property, this material can demonstrate some promising application for example, energy conversion and storage, and even some biotechnology. But for my interest, we are going to talk about the application in the electronics. And more specifically, we are going to talk about field effect transistor. This is a building block of the integrated circuit. Okay, around 5 years ago, so there was a paper published in Nature. The editor of Nature announced that the IC industry will give up the pursuit of Moore's law. That is because if we are going to continue to reduce the feature size of the transistor, the manufacturing cost will be pretty high. So the industry cannot make money from this trend. So although Moore's law is stopped, but the electronics is still developed, but their direction is changed. So people not only require the smaller device, but also require new functionalities. For the new functionality, for example, we require sensor memory, computing, and communication to be integrated together. So in this case, we need not only silicon. So silicon is very powerful, but silicon cannot do everything. If we are going to introduce this new functionality, we have to introduce some new material. So heterogeneous integration is become the future trend of electronics. So two-dimensional layered material, it is not only fundamental research interest in university, but also the interest in industry. So here is a paper published in Nature 2 years ago. That is by TSMC. Professor Philip Huang and Professor Leslie Lee, they show that the 2D semiconductor actually is also have a promising application for future electronics, even in industry. But there are three great challenges. The first one is how to predicate the property of the 2D material accurately. The second, how to grow large area, lessen defect 2D semiconductor. And the third one is how to assess the device performance with the 2D semiconductor. So let's see what's the problem with the existing transistor. In today's transistor, we are still using the 3D semiconductor, for example, silicon, germanium, and 3.5. So this material, basically, they are 3D. With the device slim down, we have to reduce the channel length. To have a very good electrostatic control, we have to also reduce the channel thickness. So, but from this 3D bond material, when we reduce the thickness, so here you can see the cross-sectional TM image. So even with the most advanced manufacturing technology, for example, silicon channel with the 0.7 nanometer, its average roughness is 0.2 nanometer. So with this large roughness, the mobility actually will be significantly reduced. When you make transistor, the threshold voltage cannot be controlled. If you cannot control a threshold voltage, when you do the design from the integrated circuit, it will generate a lot of error. So 3D semiconductor, it's already has a lot of challenge. So one possible solution is to use a very atomic level thickness 2D semiconductor. So for the 2D semiconductor, its channel thickness is just a few atomic level. So it can have very good electrostatic control. But there are still many research challenges. For example, what semiconductor channel are you going to use? So can you keep the very high mobility even with ultra thickness? Can you control the carrier polarity? Is a p-type or n-type? That is the channel. So second challenge is the contact, because the contact area from 2D semiconductor is very, very small. So how to effectively inject the carrier into the channel from the transport, how to minimize the contact resistance. These are another challenge. The third one is the interface between the semiconductor and the dielectrics. So there are a lot of trap states and also how to make a very effective electrostatic control. They are also very important. So in this talk, I will briefly talk about our study on these three respects: channel, contact, and interface. So first, let's talk about the channel. So from the semiconductor channel, actually we have a lot of choice. If you look at this period table of elements, there are a lot of two-dimensional transition metal diagonite. So the most common TMD actually is in group 6. We have MOS2, WSE2. This is the common semiconductor. But our research interest is in the group 10. So why we are interested in group 10? Because in group 10, it has a lot of D electron. If it has a lot number of D electron, it has a very weak binding to the sulfur atom or silane atoms. So in this way, the interaction will be very, very different and change the electronic property. So if the number of D electron is different, it can also affect the bad structure of the 2D TMDs. So here is the atomic structure of group 10 TMD. We study PTS2 and PTS2. Here you can see it's a crystal structure is anti-phase, lattice structure is octahedral. So this is very different from the group 6 TMD. And I said earlier, from this group 10 TMDs, the binding between the metal atom and the sulfur atom is relatively weak. So in this way, the sulfur atom, it has more active electron to interact another sulfur atom in another layer. So in this way, the interlayer interaction will be very strong. So this interlayer interaction actually can be characterized by low frequency Lyman spectroscopy. So here you can see we can measure the breathing mode force constant. From the MOS2, you can see this breath constant actually is very large. From graphene, it's also very large. That means that their interaction is relatively weak. But from the PTS2 and PTSE2, their interaction is very strong. The force constant is also very small because it's very rigid. When you do the vibration in the vertical direction, the force constant has to be reduced. We also do the DFT calculation. It clearly demonstrates the interlayer distance is reduced compared with the group 6 TMDs. So with this strong interlayer interaction, it will dramatically change the bed structure. So here we do the both optical spectroscopy and DFT calculation. It clearly see that when it's monolayer, it's a semiconductor, its band gap could be 1.8 or 1.9 eV. But with the increased number of layer, the band gap is significantly reduced. For example, from the double layer PTS2, its band gap is only around 1 eV. If we further increase to the bulk, PTS2 its band gap is only 0.25 eV. From the PTSE2, because the size of atom of SE is much, much larger, so the interaction will be more stronger. In this way, the band gap change is more significantly. So from the bulk PTSE2, it changed from the semiconductor to the metallic. So this is the first type of material. We just change the thickness. We can change from the semiconductor to the semi-metal. So this is the only type 2D material we find with these characteristics. So in this way, we can map the device with this material. For example, from the relative thin PTS2, it exhibits semiconducting property, but from the thick PTIC2, it's totally metallic properties. So from the very thin PTIC2, people already do the calculation from the monolayer PTIC2, its mobility could be much higher. So MOS2 is here, it's below 200, but from the PTIC2, theoretically, its mobility could be over 1,000. So we prepare the very simple backend FET, and we perform the characterization. So its mobility is very easily to reach over 200. We also prepare the control structure with MOS2, with the same channel thickness, same channel width, channel length, but its mobility is typically below 20. So that's verify this is indeed the intrinsic property from the PTIC2. So here you can see the comparative study between the MOS2 and PTIC2. So why is this PTIC2 has a very high mobility even at room temperature? Because its deformation potential actually is much smaller compared with MOS2. So from this theoretical analysis, you can see the wave function distribution actually is very isolated. That means the scattering, the electrophono scattering could be significantly reduced. So even the effective mass is similar to that of MOS2. So it can still reach very high mobility at room temperature. Because it can change the bed structure from the semiconductor to semi-metallic, we can also use it from the infrared detection. And also its air stability is very good, much better than that of black phosphorus. So we keep the device just in air. After half a year, it still works very well. So this is the first part. The second part from the transistor, it is contact. So contact resistance is very important to the nanoscale device because it determines the overall resistance. So usually the contact area between the two nanoscale semiconductor and the metal electrode is very small, and the resistance is very high. If the resistance is very high, it cannot exhibit the intrinsic good property of a nanoscale semiconductor and increase the power consumption. Typically, we prepare the metal electrode on top of 2D semiconductor. We use the PVD mentioned, for example, in electron beam evaporation. But when we deposit this metal electrode on top of 2D semiconductor surface, usually it will induce some defects. And these defects will generate some gap state, make the contact very bad. So we are trying to find some new way to minimize this damage. We develop a new machine that is transfer print. So we first use a standard machine to prepare metal electrode by e-beam laser, e-beam evaporation and liftoff on the silicon substrate. And then we can use PVA to pick up from the silicon substrate. And under optical microscopy, we do the alignment, and then we print on top of this 2D semiconductor. In this way, this transfer process is at room temperature. It's very mild. It will not damage the 2D semiconductor. Here you can see the a typical device we made with this machine. Here is a metal electrode. Here is our 2D semiconductor. So our collaborator, Dr. Julia, helped us to take this TM image. You can see with this transfer metal electrode, the interface between the metal and the 2D semiconductor is very clean. There is not any defect. But with this machine, we prepare device and we do the characterization. You can see by the transferred electrode, the even with the same channel thickness, channel width, channel length, we can get much higher current density with the transfer mentioned PT electrode. And we extract the field effect mobility. So you can see with this transfer metal electrode, the device can show much higher mobility compared with the device by e-beam operation. So we can quantitatively extract this Schottky barrier. So we can clearly see the Schottky barrier heat can be reduced from over 100 to 50 millieV. So this contact not only affect contact resistance itself, but also affect the electric stack control. So because from the 2D semiconductor, if at contact region it exists Schottky barrier, so when you inject the carry, there will be some region that is from the thermal assistant tunneling region. From this region, the electrostatic gate control is not that effective. So the SS will be much larger. So with the much clean interface at a smaller Schottky barrier, the thermal assistant tunneling region will be narrowed. So we can effectively inject carrier. So this is a totally harmonic region. So we can make the subthreshold close to the thermodynamic limit. That is 60 milliV per decade. So the content also affect the carry type in the 2D semiconductor. For example, in the WSC2, it has a balanced band gap. But if we use PT, it has a high work function. It should exhibit a P-type. But typically, when we use the e-beam operation electrode, it's exhibit ambipolar because at the contact region, it will induce some gap state. At the gap state, there will be some Fermi level opinion effect. So it cannot exhibit intrinsic P-type transport characteristics. But with the transfer electrode, we can remove the Fermi level opinion effect and exhibit the intrinsic P-type properties. Okay, so that's the second part of the contact to the 2D semiconductor. The third part is about the interface, between the 2D semiconductor and the gate dielectrics. So it will significantly affect the electrostatic gate control. So this equation is from the subthreshold slope. It has two atoms. One is a Body factor, is this part. The other is transport factor. From the transport factor, ideally it should be 6 milliV per decade. But from the Body factor, it is can be right in this equation. So this atom is usually positive. So in this way, the overall SS is much larger than 6 milliV per decade. But with ferroelectric gate dielectrics, we can realize the negative capacitance. With this negative capacitance, we can make the Body factor could be less than 1. So in this way, the SS could be less than 6 milliV per decade. That's the thermodynamic limit. Okay, so we design and fabricated this negative capacitance field effect transistor. We adopt the HZO, half-near-zero oxide, that is deposited by atomic level deposition process. So we prepared onto the heavily doped silicon substrate, and then we transfer our 2D semiconductor, and then we transfer our metal electrode. So here you can see the our cross-sectional SEM TM image, and also this HZO dielectrics exhibit typical ferroelectric properties. So we can realize the negative capacitor field effect transistor, both N-type and P-type. So you can see the subthreshold is below the thermodynamic limit, 6 milliV per decade. So from the P-type, it could be much smaller. It could be as low as 18 milliV per decade. So with this negative capacitance gate stack, we can effectively control the switching of the 2D semiconductor transistor. This table will list the comparison with the other device. So so we have very small hysteresis and the drive magnitude is much larger. The off ratio is also 10 to 4. So with this technology, we can construct both p-type transistor and n-type transistor. So here we use MOS2 for n-type negative capacitance FET, and we use WSE2 as a p-type NC-FET. So we use the transfer printing technology. We fabricated on the silicon substrate and then pick up and transfer to another silicon oxide substrate. And then we use a wire to connect this p-type transistor and n-type transistor in series. So in this way, we can realize a complementary inverter with this 2D NC-FET. All of the fabrication process are actually done at room temperature with the transfer printing technology. So here is the typical characteristics for n-type transistor and p-type transistor. So from the inverter, actually, you can see it can significantly reduce the static power consumption. So this is the typical NC, the inverter made with the NC-FET transistor, and this is the inverter made on some high-K transistor. So here, high-K, we just use hafnium oxide. That is the typical dielectric. It has no ferroelectric property. So here you can see from one switching, its power consumption from the NC-FET is only 68 picowatt. But from typical high-K 2D semiconductor transistor, its power consumption is much, much larger. So with this gate engineering, we can reduce the power consumption by 20 times. Okay, a quick summary. So in our work, we demonstrate some new semiconducting channel materials that has a very high mobility and high stability. And we also develop transfer print technology to minimize the contact resistance and reduce shock barrier height. We also use the negative capacitance to construct a low power complementary inverter. The static power consumption is as low as 60-80 picowatt. So that's all for my presentation. Thank you very much.
Thank you, Dr. Cai, for your wonderful talk. We'll keep all the questions and answering to the end of this seminar. Now let's invite the second speaker, Dr. Ren Kai, to present her talk.
So thanks for the wonderful talk made by Professor Dr. Chai Yang. And following his work, I would like to continue introduce you a new type of two-dimensional quantum material, which is molecular thin 2D organic and inorganic hybrid perovskite. I hope you will be able to follow me for another 20 minutes. And for the researchers who are not very familiar with two-dimensional hybrid perovskite, I would like to introduce the structures to you. So very recently, there is a review paper published in Nature Material named Emerging Perovskite Monolayers. And in this article paper, they demonstrate an possible evolution history of perovskite material. So the trend can be generalized as is from the 2D perovskite, from the 3D perovskite to 2D perovskite monolayers. And here I extract one figure from this review article to show the timeline of key milestones towards dimensionality reduction in perovskite material. So for example, as we can see, the first discovery of calcium titanate in 1839 was considered to be the origin of the perovskite material. And the material have the similar structure considered as perovskite. So subsequently, researchers began to use methyl ammonium to take place of calcium to introduce organic and inorganic hybrid 3D Perverse gas. However, due to the Goldsmith selection rule, there is a limit on the size of organic cation we can introduce in 3D Perverse gas. That is to say, if we want to continue replace methyl ammonium with a longer organic cation, the structure has go from the 3D Perverse gas to the 2D Perverse gas. Thus, in 1986, the 2D hybrid Perverse gas with longer organic cation was produced. And moreover, the first isolation of Perverse gas monolayers was achieved in 2015. Very quickly, Perverse gas monolayers, or we can say molecular in 2D Perverse gas, has very quickly played a role for the normal property exploration, and they may provide a materials platform to open up the new device paradigms. So let's take a look at the structure of both 3D Perverse gas and 2D Perverse gas before understanding why 2D hybrid Perverse gas are natural quantum material structure. So the fundamental unit of Perverse gas structure is lead halide octahedral, and this can be assembled into the 3D cubic Perverse gas structure, where the small organic methyl ammonium occupies in the interstitial cation center. And compared with the 3D Perverse gas, 2D Perverse gas shows a layered structure consisting of the inorganic octahedral sheets sandwiching by the organic cations. So the hybrid structure lead to the quantum confinement within the inorganic sheets. And as we can see in the 2D Perverse gas structure, the inorganic part act as the wells, while the organic part act as the barrier height. So because of this unique structure, the exciton binding energy are extremely high in 2D Perverse gas compared with the 3D Perverse gas. So in the 2D hybrid Perverse gas, one of very popular and typical example is Radisson-Popper's phase Perverse gas. Later, I will use RPP for short. As we can see, the formula can be generalized as this. And here, the longer organic cation are butyl ammoniums. N is the thickness of inorganic quantum well. For example, for N equals 2, it means for inorganic part, there are 2 layers of inorganic octahedral thickness. Okay, if N equals to 3, it will have the 3 layers. So from the N equals to 1 to N equals to infinite, the structure goes from the typical 2D Perverse gas to 3D Perverse gas. And when N is in between, we call this quasi-2D Perverse gas. So the first character of the RPP system is it shows a tunable structure and dimensionality by changing both organic cation and thickness of inorganic quantum well. And also compared with the 3D Perverse gas, because each inorganic quantum well are protected by the organic cations, so the stability has enhanced a lot. Another very interesting property I would like to highlight in Perverse gas system is the rush bar type spin orbital coupling. And by theory, this rush bar type spin orbital coupling is stemming from the heavy atoms. For example, in Perverse gas system, we mean the lead or iodine atoms. However, by theory calculation, the rush bar effect is expected 8 times higher in 2D Perverse gas system than 3D Perverse gas. And why moleculars in 2D Perverse gas is even more interesting. As we can see, when we decrease the thickness of a material system, for example, from the bulk to monolayers, usually the surface effect will stand out. And also, compared with the rigid inorganic quantum well, just as Dr. Chai has introduced. The 2D perovskite monolayers with only a few nanometers thickness, it is a really soft material. And in this case, we can imagine that the string can easily to be introduced to modulate the property of the perovskite monolayers. And also, like graphene, perovskite monolayers can be very easily to be operated to the following device fabrication. So it may open up a new device paradigms. And we have published a review paper to elaborate our viewpoint on this emerging research field. Okay, because previous study depend on perovskite are mainly focused on spin coating film, polycrystalline film. So the thickness dependent study are always overlooked. And here in our review paper, we would like to highlight a new concept is 2D perovskite with different thickness can find their own niche for different applications. For example, for the thicker or bulk crystal, the photorecycling effect is presented, which resulting in a redshift appeal emission peak. And on the contrary, for the thin flake with the thickness between 20 to 90 nanometer, the photorecycling effect is surprised, and the non-linear optical effect is stand out. And for molecular thin 2D perovskite, due to its ultra-soft nature and good electrical permeability, it is the ideal material for the nano or macro device fabrication. For example, we are the first to report that the highly enhanced third harmonic generation was presented for RPP flakes at the thickness around 90 nanometer. For example, as shown in the pictures, the exfoliated RPP flakes with a thickness range from only a few nanometer to hundreds of nanometer was exfoliated, covered by or protected by a few layers of transparent brown nitride. Then, based on the color mapping result, we can see the strongest THG signal is neither achieved for the thicker flake or the molecular thin 2D perovskite. It is only achieved for the thickness around the 90 nanometers. Okay, now let's enter the world of the perovskite monolayers or molecular thin perovskite. So, as the top organic cation is very easily to be damaged under the external stimuli, for example, the laser illumination. So perovskite monolayers itself is not very stable for the optoelectronic measurement. In our work, we have demonstrated a stable platform, which is the 2D perovskite monolayer covered by only a few nanometer transparent brown nitride. Later, I will use HBN for short and this stable system allow us to explore the intrinsic property of the 2D perovskite monolayers without any risk of surface structure decomposition. So firstly, we highlight the exfoliation method to produce 2D perovskite monolayers. This is because compared with the solution prepared method, exfoliated method are trusted to produce perovskite monolayers with the cleanest surface. This is very important for us to see the intrinsic property in 2D perovskite. As we can see, taking bulk nickel to RPP as an example, the two layers of organic cation are interlocked by the van der Waals force. So this weak connection force allows us to use mechanical force to detach these two layers of organic cation. After exfoliation, only leaving one layer of organic cation on top in perovskite monolayers. And In order to produce the Perverse monolayers, firstly, we grow the centimeter size RPP single crystal by a temperature programming method. And relying on this phase pure and large size RPP single crystals, we could exfoliate the Perverse monolayers with a lateral dimensional between 20 to 100 micron size. As we can see, the height profile obtained by AFM measurement agrees well with the C-axis lattice result by the single crystal SRD from n equals to 1 to n equals to 4. Sorry. Surprisingly, our Perverse monolayers shows even enhanced crystalline quality compared with the bulk single crystal. As we can see from the PL emission, Perverse monolayer shows the narrow line widths, and also compared with the bulk crystal, they show the smaller stroke shifts. And relying on this very high quality single crystal Perverse monolayers, we have observed a reversible order to disorder transition in Perverse monolayers, which is absent from their bulk counterpart. So as I mentioned before, the surface structure of Perverse monolayers is very easily to be deformed under the external stimuli. So here, under the laser illumination by covered HBN, we see the surface structure of the Perverse monolayer began gradually disordered, which is manifested by a gradually redshift PL emission peak. Most interestingly, this entire PL evolution can be totally reversed if the sample is subject to higher laser irradiation under the vacuum. So we also call this reversible process as reversible exciton state in Perverse monolayers. And based on the PL color mapping result, we can see this reversible spectral redshift process can be well repeated for several cycles. And we also carried out the thickness dependent for the magnitude of PL redshift exploration. As we can see from n equals to 1 to n equals to 4, n equals to 4 shows a smaller redshift window. So do you know this is why? Because as I mentioned, from this structure, n equals to 4 has the thickest inorganic quantum well. So most interestingly, we have captured the visual evidence of this order to disorder transition by non-contact Q plus AFM. In fact, it is not very easy to capture the atomic structure of the 2D Perverse considering the top organic cation. So the traditional TEM or STM's characterization method is not very suitable for the Perverse monolayers. This is why we choose the non-contact Q plus AFM technique to see the perfect structure of Perverse monolayers. As we can see, if we look at the structure of the Perverse monolayers from the top, it shows the square pattern organized by the organic cations. And by introducing the T pressure as one kind of external stimuli, the order state leads to the disorder state, which is manifested by the zigzag chain pattern. And after releasing this T pressure, the disorder state go back to the order state again. So which indicate this process is also a reversible process. Moreover, to simulate the laser annealing effect by the laser irradiation, we carry out the in-still valence band structure measurement to understand the in-depth physics. As we can see, upon increasing the temperature, the relaxation state has increased. This is manifested by the zigzag chain. And this relaxation state based on the valence band study help to increase the intensity of density of state near the Fermi level. This indicates there are more trap state has been increased in the surface of 2D RPP. And this help to compress the recombination rate by trapping one particular of free carrier, for example, the hole or electron, then to increase the photo gain. And finally, we have, fabricated the Perverse field transistor based on monolayer, bilayer, and bulk. As we can see, firstly, in one device, we can reversibly control the realization state and derealization state. And we have found the photocurrent from the realization state is always higher compared with the derealization state at the same laser intensity irradiation. And by comparison, the photocurrent performance among monolayer, bilayer, and bulk, we found that the highest performance that internal quantum efficiency is achieved in molecular scene 2D perverse sky. This is due to the good penetration of electric field in the thinner flake. Now let's look at the structure of the perverse sky monolayers again. So here the top organic cation act as the high dielectric barrier will introduce the very high contact resistance or interface resistance. So this is why the field effect transistor result or data is, work is rarely reported in 2D perverse sky compared with the 3D perverse sky. However, this is not to say the top organic cation do not have any advantages for device applications. Actually, it can be used as tunneling barrier in spintronic devices study or construction. And we have found the charge injection barrier changes depend on the electrode in the FET devices. Later I will explain. And also, because due to the rush bar effect, the inorganic part can introduce a spin. So 2D perverse sky monolayers can be explored as both spin generator and a charge injection barrier in the future spintronic devices application. And we are the first to report the field effect transistor based on 2D RPP. And understanding the electron tunneling through RPP and electrode interface. Actually, choosing the right electrode is very important to make your FET device works. And in our work, we choose the gold and graphene electrode as a comparison. As we can see, based on the work function, alipsometry, and valence band study, we are the first to show the energy diagram based on the real experiment data among 2D RPP gold and graphene. As we can see, the conduction band of 2D RPP is near the Fermi level of the graphene. And in this case, the charge injection from the graphene to 2D RPP should have a low bias. On the contrary, the Fermi level of the gold lies into the 2D perverse sky. So the charge injection should have the larger Schottky barrier compared with the graphene contact interface. And we also use the scanning tunneling microscope to understand the tunneling barrier and the domain size before we construct the devices. In fact, it is still not easy to get the STM image in 2D perverse sky because the very high contact resistance in the top exists in the 2D perverse sky from the top organic cation. However, the STM image is the measurement to reflecting the electron tunneling result, right? So as we can see, the STM image we got shows of RPP shows the typical paired structure formed by the nearest neighbor iodine atoms. And a lot of information we can get from the STM. For example, as the size of single domain increased with the thickness. As we can see, the monolayer on graphene shows more domains with different direction compared with bilayer and bulk. This is because, I think it's because the substrate influenced the string reflected on monolayers, even though we think that graphene is a very smooth material. So this is why I always mention the perverse sky monolayer is ultra soft, right? So Another information we can get is a higher degree of the surface crystalline we always observed for the RPP on the graphene compared on the gold. And this may be the reason why when we carried out the STS measurement, we can see for the flake with the same thickness, the tunneling gap is always higher for the gold contact compared with the graphene contact. And also when we keep the substrate as the same, for example, graphene contact, when we decrease the thickness of Perverse guy, the tunneling barrier has decreased. So based on the above information, finally we choose bilayer RPP to transfer onto the Perverse guy, graphene electrode to construct field effect transistors. And based on our result, I would like to highlight 3 points which is not reported before. Firstly, our 2D RPP shows the electrode-dependent transport behavior, which is N-type for graphene contact, while the P-type for gold contact. And as we can see, the source stream current is always high for graphene contact compared with gold contact. When we increase the temperature, for example, from 1.7K to 100K, the source stream current has decreased. This is different from the behavior from transition metal dichalcogenate. Do you know why? This is because the ion aggregation in the small organic group in the 2D Perverse guy. And in order to elaborate the charge injection mechanism in the 2D Perverse guy, we show the further diagram here, which is extracting from the output curve. As we can see, the injection mechanism shows a gate tunable behavior, which is the direct tunneling at the low voltage to FN tunneling at the high voltage. And here the transition voltage is related to the barrier height. So we have observed a much higher barrier height for gold contact while compared with the graphene contact. And most interestingly, upon the laser irradiation, our photo FET shows the output of photo FET shows the behavior from the nonlinear to linear. Okay, this is because a lot of free carrier has been created under the laser irradiation, thus to reduce the Schottky barrier widths. And we also carried out the transport character as a function of laser irradiation. As we can see, when we increase the power intensity, our device cannot be gated anymore. This is because there are thousands of free carrier has been created to make our device cannot be gated. Okay, very recently, we also published another feature review paper to highlight another very promising property in 2D Perverse guy. And I would like to say the research based on moleculars in 2D Perverse guy is still in very early stage. And here we think because of the unique structure of the 2D Perverse guy, the order to disorder transition of the organic cation drives the pyroelectric to ferroelectric phase transition. And this cannot be seen from the 3D Perverse guy. And also we highlight the concept that to modulate spin polarization by electric field caused by the ferroelectricity, we can make the self-power spintronic devices based on the 2D Perverse guy, which is very promising for the future device application. Okay, finally, I would like to give a summary. Through my presentation, now you may know the moleculars in 2D Perverse guy is a new type of 2D quantum material. And when we decrease the thickness of a material system, normal properties are always presented. What we have observed is order to disorder reversible transition. And based on this normal property, we have demonstrated the field effect transistor, photodetector, and possible spintronic device. Okay, I will stop here and thank you for your attention.
Thank you, Dr. Leng, for your wonderful talk. Now I will invite the third speaker, Dr. Huang to
to give his presentation.
Good afternoon, everyone. I'm Dr. Huang Bolong from ABCT department. I'm very happy to join this FAST seminar and share my recent research of 2D materials with you. So I will talk about the theoretical study on optoelectronic properties of 2D dimensional materials today. So in recent years, the low-dimensional materials have attracted intensive research attention. They commonly use graphene, black phosphorus, and TMD, boron nitride, carbon nitride, all belong to 2D materials. And they have shown superior properties in many different applications, including energy conversions and optoelectrical devices. So 2D materials display not only the unique electronic structures and physical chemistry properties, but also flexible modulations in real space nanostructures and also the reciprocal electronic structures. These properties enable us many functional application in the materials, especially for the ultra-thin optoelectrical materials. Meanwhile, the 2D materials have shown remarkable mechanical stabilities, which further expand their applications in flexible electronic devices. So therefore, from the 2D materials, there will be the significant directions for the developments of the novel functional materials now and in the near futures. So in 2D materials, transition metal dicarbonized, TMD, is one of the most important one. So this type of the materials usually shown in layer structures with weak interlayer interactions, such as van der Waals interactions. So in the particular, monolayer TMD materials have shown unique electronic and optical and photonic and piezoelectronic properties, so which have enabled wide applications in energy storage and conversions, and also the optoelectronic devices applications. Meanwhile, this type of materials also allows the flexible modulations methods, including doping and heterojunctions, to extend functions and achieve the desired properties. In recent years, the TMD materials and 2D oxide materials have also achieved a significant progress and revealed many unique properties. So including the Vallée Hall effect, Vallée polarization effect, and superconducting, electricity, and piezoelectronics. So these works all confirm the promising future of the 2D materials in this field. So currently, several strategies have been developed for TMD materials, especially the properties modifications. It usually includes the intrinsic defects, heterojunctions, heteroatom doping, alloying, etc. Moreover, the controllable force control in GNS structures further extend properties. However, although the strategies have carried out intense experiments and characterizations, their influence on their detailed electronic structures are not well understood. So therefore, in this talk, I will mainly focus on our recent works in electronic structures of 2D materials from the atomic levels. So first, in the most common TMD heterostructures, in the two-dimensional monolayers scales, the repro effects at the interface have been noted in many works. Such an unique repro may come from several possible mechanisms, such as a mismatch of the lattice structures, the electron couplings and phone interactions at the interface. So far, all the evidence come from the experimental characterizations. So therefore, we hope to use the theoretical calculations to supply some insightful information of structural evolutions and electronic structures for the synthesis and modulations of the TMD synthesis. First, we have constructed several TMD heterostructures with different anions for the phonon dispersions. The phonon dispersions reveal the lattice vibration mode of the materials in a wide range, the frequencies of the vibrations, compared with the phonon dispersions of single TMD materials. the introductions of additional anions cause different influences on the lattice vibrations. Within the heterostructures, the interaction between the sulfur and the seleniums, even the tellurians, are able to include the image frequencies at the highest symmetrical points of the structures. This is the indicating potentially the instabilities of the lattice mismatchings. So this confirms that interactions of the anions and interface are capable to enlarge the instabilities of the structures, which further results in the repro structures at the interface. So due to the perturbations induced by the anion interactions, the lattice structures will also be affected. From the classic potential view, the heterostructure is able to include in the superstructures. Our theoretical explorations have observed this gradual lattice change. So this is like snowflakes, such superstructures have been noticed in the different directions and periodicities. And these structures is attributed to the pp couplings of the orbitals in the selenium and sulfurs interactions rather than the so-called two-dimensional in-plane quantum effect induced by ultra-thin structures. So similarly, we notice this the ripple-like the structures and the interface of the superstructure is more like electron phonon couplings, as well as the string disturbance by the anion charge density disturbance. Meanwhile, we also need to investigate the influence on the electronic structures, including by the interface of the pp couplings of the orbitals. So from the analysis of the density of states, we notice the tailing states near the Fermi level induced by the pp couplings of the orbitals of the sulfur and selenium coupled. So this confirms the effects of the electronic structures is also the essential factors to modulate the mechanical effects of the in-plane phenomena. So through the zoom in the structures, we are able to observe the structural evolutions of the lattice structures from the original superstructures. Based on our works, we have proposed the elastic perturbation entropies, which is able to estimate the quantifying the rod size of the repro structures based on different structures. And we have achieved in exploring the two-dimensional heterostructures from the atomic levels. So then what we see from this slides, we have further enlarged the theoretical models in a larger size from several tens of the angstroms to several tens of the nanometers, or even approaching to the trying to approach into the micrometers scales. So we have constructed arrays of the heterostructures such as corresponding the experimental observations according in atomic force and microscopic scales. Similarly, the repro structures is still able to notice at the interface. So meanwhile, such ripples shows certain levels of the periodicity, which is affected by the interface scale and anion ratios. So within the increase of the arrays, the compression strain mainly located at the interface of the heterostructures. So the triangle array centers shows the tensile strains. And inside triangles, within the induced strain effects, the formation ripple may be further accelerated by in triangle the compressor strains and outside of the tensile strains, the competitions. So also the strain effect will significantly modulate the electronic and optical properties of their materials systems. So in the end, we apply the so-called console softwares to reproduce the heterostructures with the same size of the experiment. At the end of the interface, as at the edge end of the interface, we find the boundary effects is also interesting. We notice that in repro formation still exists, so which means it's a large scale extending in the general behaviors. It's such as a long range orders beyond the 10 angstroms or even approaching to the microscopic micrometer scales. So meanwhile, the repro scale will be affected by the interdistance of the arrays. So this is the manufacture features, especially we are modulating the real space structures in a single molecular layer theme on 2D-dimensional electronic structures. It will induce the ripple effect, could be substantially induce the electronic channels with a couple molecules length longs. So the medium scale simulations, the strain effect still show the tensile strain in the triangles and the strong compression strain at interface. And then the next interesting systems, it is we'll introduce important works about the atomic mappings about the two-dimensional indium selenide materials. So although low-dimensional materials show the unique properties, lots of microstructural informations are challenging to obtaining during its characterizations. Sometimes, even we have obtained some informations, we cannot directly relate them to the specific structural features, such as the intrinsic defects. So such defects are critical to the low-dimensional monolayer TMD in both structures and properties. And the originations about these kind of defects will generally coming from the synthesis process and layer by layer MBE effects, so-called molecular beam epitaxial effects, and also the tip effects by the scanning tunneling microscopies. So targeting on this kind of intrinsic defect induced monolayer surface effects, we have carried out some exploration from scanning tunneling microscopy simulation and phonon dispersions and electronic structures. So from the fundamental electronic structures, we noticed the uneven electronic distributions. So this indicates that the monolayer indium selenide show the natural preference towards the polarizations, which is easy to affect by the external field. So from the phonon dispersions, the layer numbers is highly correlated with abnormal phonon shiftings, especially in the gamma points of the optical branches about the phonon dispersion spectrums. In some symmetric points at unique discontinuous kinks identifies these materials for potentially using in different layers, suggesting existence of the core anomalies in the structures. So which means the two-dimensional indium selenides in some specific direction preference, it will induce the elastic ballistic transportations of the electrons in these two-dimensional monolayers about indium selenides. So since core anomaly usually appears in the metals, such electron phonon coupled unique phenomenon we observe by our theoretical studies. It could be the originations about the strong ferroelectricity, or in the future, high temperature superconductivity in the monolayer indium selenides. So in the current two-dimensional ferroelectricity materials, the scanning tunneling microscopic method is also very important. This is so far what we get is an atom by atom images in the highest resolutions compared to the other HRTMs. And STM is also a very ideal tools, can be atom by atom modulating based on these atomic scales applications. So we also carried out the simulated STM on different indium selenide structures with different intrinsic defects. So we notice high sensitivities of the STM on a lattice change, especially the intrinsic defect like vacancies, interstitials, the atoms. It is an effective way to view the local structure change as well as the charge densities of the surface. So therefore, we can supply a comprehensive libraries of the structural information in two-dimensional materials, which can become a good reference for experimental characterizations. So for the common selenium vacancies, the charge fluctuations near the defective areas is noticed. So which leads to the strong contrast by our simulated scanning tunneling microscopic images. So this can be also observed by the experiments. And we will show them these slides in the later slides. And in the additions, we have noticed the long-range PP couplings of the orbitals again induced by the interaction between indium and selenites. So this information can become the evidence of the support the experimental characterizations in the future of some specific structures about the within the TMD scales. So in the meantime, the cation vacancy is also important because it actually does not follow the exact stoichiometric ratios from the chemical compounds in the selenites. So the indium vacancy is also able to cause the strong charge contrast due to the electronic perturbations. And the formations about the indium vacancy will interact the electrons in the pp sigma bonds between the indium and the selenite. So for both cation and anion vacancies, the long-range pp coupling orbitals will not be affected at all in the two-dimensional scales. So through the previous result, so the simulated STM is capable totally and to reveal even the subtle structural change. And therefore we can totally be able to construct a comprehensive library of their full defects in the structures. And this library has revealed many interesting informations for this kind of two-dimensional electronic materials. For example, the selenium vacancy clusters is able to induce the electron couplings on the surface, such like tri-selenium vacancies. And also the anti-side defects cause a strong and long-range electronic perturbations on the surface, which could initiate the surface reconstructions or the phase change. So the library clearly distinguishes the influence of the different defects. It will become the highly useful tools to supply significant information and references for the understanding the microstructures of different materials. So this will inspire us to build up this kind of library in the big data space for the intrinsic defects, considering all kinds of possible combinations about the intrinsic defects during the synthesis within the range of the two-dimensional materials. And also consider the limitations about the experimental range from the 4 Kelvin to the room temperatures, covering from the liquid heliums to liquid nitrogens temperatures. We are totally capable to simulate all wide temperature range of the STS. So beside the simulated STM images, we can simulate the scanning tunneling spectroscopy based on our service P dots, also oversize the significant information for comparison. So therefore, from these pictures, our theoretical calculations not only can supply references and formation to the experimental groups, but also offers the in-depth discussions on the electronic structures and orbital couplings. This will totally and flexibly supply the comprehensive and synergy comparisons for recognizing the surface constructions and surface intrinsic defects for the defect-related modulations of the electronic structures in 2D dimensional materials. And one step further, we have a collaboration with Professor Lo Tian Ping from Singapore in US. So recently the works are accepted, which previously submitted to the Nature Nanotext. We have experienced 2 rounds of their peer reviews. And this work is very interesting and also significant for the breaking through, because we also find the beta prime of the indium selenites have been found in many experiments. And during these experiments, we have identified coexisting of the beta prime and the beta prime double prime phase under the scanning tunneling microscopy. When we scanning this, it will real-time spaces phase change on the different bias voltages. And this beta prime phase have been identified and discussed before. However, the beta double prime phases have not well understood and also have been extensively reported before. And preliminary data in this collaboration projects, our theoretical calculations have proposed these structures of beta prime phases combined with the beta double prime phases. So these 2 phases have shown different electronic structures. and which leads to different optoelectrical properties in applications, also the intrinsic properties. In the beta prime phases, we have noticed the two opposite polarization directions which balance the overall polarizations. And this indicates the anti-ferroelectricities of the beta prime phase. Meanwhile, the beta double prime phase display the show the high disorder with non-balanced polarizations. And this totally leads into the potential of the ferroelectricity generations. The slight structural change in the two-dimensional indium selenides has actually turned out resulted in completely different electronic structures. And to verify our proposed structures about the beta double prime phase, and our proposed structures of the beta double prime phase, we have simulated the scanning tunneling microscopy to compare the experiments. Meanwhile, we have noticed 3 different levels of charge distributions indicating different electronic couplings. It is noticed that the strong contrast form the zigzag pattern, which is consistent with our experiments based on Omicron whole set scanning tunneling microscopy and scanning tunneling microscopies, spectroscopies given by NUS team. So in the end, we have compared the formations energies about both phase indium selenides. It is noticed that beta double prime phase shows a lower formation energy than the beta prime phase, indicating the high stabilities. So this also supports formation of a conditional about the beta double prime phase in experiments. And meanwhile, the optical properties based on the dielectric functions also confirm that, and these 2 phases show highly distinct electronic structures, totally can be measurable based on the ordinary optical techniques. In the end, we have also investigated 180-degree polarization switching in beta double prime phase. It undergoes a small energy barriers about 0.42 electron volts. This is typical numbers we predicted based on the conversions from the mixed polarization directions to strongly polarizing the one directions, and recently confirmed by another experiment projects, and we are prepared. In the end, we will introduce the 3rd interesting systems. What we found is studied core anomalies in the graphene-like monolayer zinc oxide. So the core anomalies, again, we talking about these keywords usually existing in the metal, which is the electron phonon coupling in phenomena, and also the indicator about the superconductivities. And the core anomalies will further affect electron transfer and speed and features in the ballistic transportations. So also normally found in non-metal materials like the carbon nanotubes or graphenes. So this phenomenon can be identified through the unusual kinks of the discontinuity of the phonon dispersions. However, while we need to find now the zinc oxides, it actually is another space correlated. Actually, it's a temperature correlated. So now what we need to innovatively to change these techniques and frameworks of the theory investigations. So we have carried out a high precision phonon dispersion from 4 Kelvin to 800 Kelvin for these materials. And as we know, zinc oxide in a graphene-like layer is not easy to obtain by experiments. So we are also collaborating with the Beijing teams from Professor Zhongling Wang. So the phonon dispersion have shown a strong sensitivity of the temperatures, what we need to consider in that. So when we found at 300 Kelvin, we noticed abnormal drops of the discontinuity, so which is attributed to the existence of the core anomalies. Based on the Fermi Dirac functions, we further identified the discontinuity points of the phonon dispersions at specific temperatures. So in the low dimensional zinc oxide, the temperature is 300 Kelvin, which is very close to the room temperatures. And this continuity point can be found in the phonon dispersion in the temperature space, not in the wave vector space. So this is abnormal and with our high precision calculations. And this is also the first time that we notice such a phenomenon in wide bandgap semiconductor materials instead of the metals, also the graphene-like materials. So therefore, we further propose the elastic perturbation entropy and to discuss these phenomena. We think that the EPS, elastic perturbation entropy, EPS, shows a strong quantitative correlation with the local electric fields induced by the perturbation electrical charge. So the Carr anomaly will largely enhance the charge and also the EPS through the high electrical response. Through the series deviations, we propose the equation about this elastic perturbation entropy as a criteria to screen out the currently possible materials with the Carr anomalies and also a good candidate for nanogenerators. So we have carefully compared with low-dimensional materials and bulk materials. So the phonon dispersion in bulk zinc oxide will be sensitive to the weight factor Q rather than the temperatures. So this is the in bulk materials. As we know, bulk zinc oxide is famous for the intrinsic defects like oxygen vacancy, which is a mission impossible for the nanoscale synthesis. So this is why we hardly to observe these Carr anomalies in the oxide materials. So, but we never stop these efforts because Carr anomaly will significantly reduce these degeneration effects and meanwhile enlarge the response of our piezoelectronic effects, which means we are substantially large in the future applications in electronics. So in the bulk zinc oxide in the zinc diacarbonate materials, the phonon dispersion shows a much lower sensitivity to the temperatures. So again, the Carr anomaly, that's why will become less evidence induced by the intrinsic defects in the bulk materials. So this represents that low-dimensional materials with the strong Carr anomalies may cause the surface phonon instabilities for further formations of the defects. And we have also applied STM simulations to characterize the defects in low-dimensional zinc oxide. The surface instabilities has induced the oxygen intrusions, which further leads to the formation of our defects and the surface distortion. This will induce us to find the Carr anomaly actually can be overwhelmed by surface defects again in the two-dimensional scales. So with such surface distortions or defects, the surface reconstruction will also be initiated by the disturbance in the mechanical scale. In another two-dimensional materials, we have also noticed the Carr anomalies like lithium nowadays, but it is now working on the projects. In areas of the zinc oxide nanotubes, we observe the phenomena of a coolant exchange correlations. And such interaction induced array twisting and further increasing the piezoelectronic effects will supply important theoretical references for the nanogenerators developed by Professor Zhonglin Wang. So in the end, we will summarize our recent works in the two-dimensional materials. And in a different two-dimensional materials, we have identified the significant influences of the electronic couplings and the perturbations. So theoretical calculations actually can supply the STM library to help experimental groups to understand and the microstructures and even phase change of the different systems. For example, that's what we call the beta prime and beta double prime phase of indium selenide. And to modulate the optoelectronic properties, there are three main different modulation strategies, including the electronic structure modulations like the PP orbital couplings and intrinsic defect modulations, for example, deviation about the stoichiometric ratios about their surface. And also the phonon property modulations, for example, like the electron-phonon couplings about the defect given by the anion disturbance. So in the future, we will keep carrying on the theoretical calculation efforts on the more two-dimensional materials for broad applications in real space modulations, as well as the two-dimensional electronic structures in electronic structures in the reciprocal spaces. So this is all for my presentations for today. Thank you.
Okay, maybe I ask the first question. I would like to ask Dr. Ren, in the Robertson proper sky structure, is there any limit for the number of N? N is the number of inorganic layer.
Yes, okay, thanks for the good questions. Actually, when n equals to infinite is go to the 3D structure, based on the paper has result experimental. Usually now we have synthesized crystal for n equals to 5. N equals to 5.
Okay.
The single crystal we can got based on the experimental data.
And in experiment, how to control the normal way?
How? This is based on the chemical ratios you have used. I mean, to control the precursor ratio. For when we grow the single crystal, there for 2D perverse sky, there are 3 chemical precursor we should to use. So by control the molar ratio, we can got the different n values.
Okay, and also if you have shown you make a 2-dimensional layer of the RPB, right? And
Yes.
It seems the terminating layer is the organic layer. So
Yes.
and if you get this 2D layer from the exfoliation of bulk material, then there's also opportunity, right, to get a terminating layer of the inorganic layer. So why you get it?
No. It, because what we use exfoliation, we can only exfoliate, break the force, right? Because the organic and inorganic part are connected by the iron force. Iron force is very rigid compared with van der Waals force. So when we do the exfoliation, we can only break the 2 layers of interlocked organic cation between 1 layer of organic cation on top. Instead, we cannot break down the organic and inorganic interface. Do you understand what I mean?
Yeah, I see.
Thank you.
Okay, thank you. Okay, maybe I ask the second question. If not, I'd like to ask Dr. Huang Borong. You have showed us the atomic mapping of the ferroelectric 2D material, and I would like to know, have you also identified the direction of the polarization?
Yes, and these preliminary studies, we're trying to optimize the directions in the in-plane and out-of-planes. So, which means vertical to the in-plane surface in the Indian selenites. And for the 180-degree conversions, polarizations, we have another angle-related electric function modulations in these simulations. But we haven't not actually shown these results because this is kind of a tensor result.
Okay, is it also possible to determine the magnitude of the polarization?
Yes, we can, because this polarization simulation depends on finally the frozen structures combining the electrodensities of the 2-dimensional surface. So this is totally can provide the magnitudes and the directions in the tensor scales.
Okay, thank you.
Thank you.
Okay, while we are waiting for the question from the audience, I'd like to ask my third question. I'd like to ask Dr. Chai, and you mentioned in your PTSE, I remember, or PTS2, you have mentioned you get a very high mobility, and you also mentioned the charge density are quite separate. Or
not density, it's a deformation potential. That is representing the electron interaction.
Okay, so if you have a very high mobility, then the charge density from different atomic size would overlap, right? Instead of the isolated one.
Layer dependent band gap. So when you have overlap on the wave function, the band will be split. So originally from monolayer PPS, its band gap is relatively high. It's
will manipulate. If you have a two layer, you overlap, the bed will be split. So from the conducting bed will going down, then bed will go up. So in this way, the bed gap will reduce. So with the Monolayer stacked, bed gap will be smaller and smaller. Okay, thank you.
Thank you. Very nice talk. I have two questions. One is from Dr. Cai Yang, and another is for Dr. Huang. For Professor Huang, Professor Cai, I'm very interested in the negative capacitance of the 2D materials, the interface between the 2D materials and the dielectric. Do you think the main application of the negative capacitance is reduce the power consumer, right?
Okay, so for the negative capacitance get stack, so actually it's a ferroelectric material. So with this get dielectric, you have an internal amplification of get voltage. So for example, we will apply one way. It could be amplified to be 1 point something. So in this way, it can have a much better electrostatic gate control. So with a better gate control, you can reduce the subthreshold slope. So that means that when you switch a transistor from on-state to off-state or from off-state to on-state, so you only need to supply very small voltage. If the voltage is smaller, the power consumption will be small.
Okay, thank you. And another question for Dr. Huang. You show very excellent calculation results on the 2D dicapitogenide materials. I wonder whether you have tried to do the calculations on 2D oxides to oxide materials, and where is the challenges for the 2D oxides, like for example, the perovskite oxides, and have you tried or interested in the infrared frequencies of the 2D materials?
Thank you very much for the question. Actually, we have tried the zinc oxide as a related materials in the graphene-like monolayers. Actually, we often can try the pyramid protruding zinc oxide and also the other oxide materials and beyond the TMD material selections in two-dimensional scales. Actually, we are capable to simulate the electron couple structure, electronic structures, presentations, and also the phonon spectrums in the dispersions and the density states of the phonons. And we can also reflect the in infrared scales in optical branches about the phonon dispersions behaviors. So this will totally capable to carry out some. Actually, we collaborate the inorganic or organic like oxide as well as the even the perovskite materials. So to do that, I think if you also have this kind of interest, I think we can have this team-based collaborations for this, so that we can more focus on the electronic structure modulations, and also the teams can also capable to do the device application. Will be a more ideal combinations in this project.
Yeah, got it. Thank you very much.
Thank you.
If no more questions, I would like to close this session, and thank you once again, Dr. Cai Yang, Dr. Len Kai, and Dr. Huang for your sharing this afternoon. I would like to also thank our colleagues for joining the seminar today. There will be the second seminar on material science on 30th of July. We look forward to seeing you again in this seminar. Thank you.
Thank you. Bye-bye.
Bye-bye. Bye-bye.